Hi everyone, welcome to Om Learning Lab. In this video, we are going to solve the problem binary tree maximum path sum. This is one of the problems in LeetCode's set of 150 problems for coding interviews, and it is a hard category problem. Without any further ado, let's get into it. So the problem starts with a definition of path. So a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them, pretty standard. Then they say that a node can only appear in the sequence at most once. So there cannot be any repetition of nodes. This is important. Note that the path does not need to pass through the root. We will come to this point later when we go and take a look at the examples. Then finally they say that the path sum of a path is the sum of the nodes values in the path. Given the root of the binary tree, return the maximum path sum of any non-empty path. So for example, in this particular tree, it is very obvious to see that we need to take all the nodes 3 plus 1 plus 2 and the output is 6, which is the most optimal sum, right? So if I take 1 only, it is less. If I take 1 and 3, it is less. So taking all the nodes is optimal. However, this is a better example and we'll start working on this example and build some examples of our own to try and understand what should be the correct approach to solve this particular problem. Let me try to replicate this particular problem, this particular example in the notebook, and we'll try to understand. We'll try to understand the problem through this. So we have minus 10, 9. Let me just try to replicate this. I'll go to the notebook, full page view. Let me start drawing. So I have minus 10. I have a 9. Then I have something over here, something like 10, 20, and a 7. Cool. This is the binary tree that I have. And here, if you go back to the example and see, this is the most optimal path, right? This is a valid path because, 3 nodes are involved, nothing is repeating, and this sum is maximum. One can notice that any other type of combination that we take for this particular tree will be suboptimal. For example, let me try out some other combinations in green. If I take these two nodes and this, it's of course suboptimal because minus 10 is present. 7 is of course better than minus 10. Similarly, if I try to come over here, it is still suboptimal because minus 10 plus 9 is still minus 1, and still this involving 7 is a better choice rather than going over there. But however, if let's say here I had something like 11, let's just say, now the better path would change. Our answer to what is the best path would change. Why? Let me use pink for this. In this case, the best path that we could get would be this one, right? Because if I involve 11, 20 plus 10 is 30. I was involving 7 originally. Now in place of 7, I have minus 10 plus 9, which is minus 1. But there is this 11, which is giving me a plus 10, making it the most optimal. Let me draw this once again so that this clutter goes away. So I had minus 10, 9, 10, 20, and 7. So the idea is that if I'm looking at the tree from the root node, from the right side, I can get two kinds of values, and understanding this is the crux of the problem. If I go back to the problem, what they are saying is that they define the path and then they say that the node can appear at most once. That we are taking care of. And another important point to note here is that, definition of path is important because we can make a mistake while solving this problem. That is, For example, if I go back to this particular notebook, you see, for example, let's say I had, what can I do? So let's say instead of 9, I had something like 11. Okay. In this case also, it is important to note that in this case also, this is the most optimal path. This is the solution. Why? One cannot say that this entire thing is the path. Like you include 11, you include 10, and then the rest of the tree. It is not a path. So that's why they have defined path explicitly. That is, it is a sequence of nodes with edges connecting them, and a node cannot repeat. So we cannot be like, you include this node as well, this node as well, this node as well, and all the nodes. We cannot do that. That's not a valid path because this node will repeat. So that is not allowed. So that's why, to drive home that point, they have explicitly defined what a path is, and they have also mentioned the condition that node can appear at most once. Now, keeping that in mind, you need to understand that the crux of the problem is when you are at any particular node. For example, you are here, you can get 4 kinds of values. You will get 2 kinds of values from the left side, like the left branch of that particular node, and you will get 2 kinds of values from the right branch of that particular node. What are those 2 values? One kind of value represents what is the most optimal sum if this is involved in the path. The root node is involved in the path. And the other is what is the overall max which is possible. So again, I'll have to draw the tree because this is one of those problems where we have to try and visualize as much as we can. So if I have to draw the tree repeated multiple times, so be it. I don't mind. So this is our binary tree. What I'm trying to say here is, now that we have understood what a valid path is, what they mean by why they have mentioned the condition that a node appears at most once, what we need to understand is, for any particular node, let's say this, it will get 2 values from left and it should get 2 values from right. Why 2 values is, we need to track what is the overall max that it can get from each side and what is the max possible value if this is included in the path. What that means. So for this particular node, if I consider this branch, let me use pink color for this branching part. I'm looking at the right branch. Okay. What is the overall max that I can get? Of course, overall max is include these 3 nodes, 10 plus 20 plus 7. So my overall max will be something like, 30, 37. 37 is the overall max I can get from right hand side. But what is the max value that I can get from this branch if I want to include minus 10 in the path? So we'll have some choices, like we can have minus 10 and 10, like 10 and minus 10, that is a valid path. Or we can have 20 plus 10 and minus 10, that is a valid path. I'm talking about this path. Or we can have 7, 10 and minus 10. Please note, we cannot have all these 3 and minus 10 included because that will be an invalid path. 10 is repeating twice, hence the definition given by them. So the possible paths from the right branch for this particular node such that minus 10 is included are either only 10 or 10 plus 7 or 10 plus 20. Of course, which is the most optimal one? 10 plus 20. So we'll pass that as well to this particular node because it needs to know that, okay, for this particular node, what is the overall max that I can get from the right branch and what is the max I can get if I want to include this node. Why that is important is, for this particular example, 37 is the answer. Definitely, there is no doubt about it. However, there could be a situation in which it will not be the answer. For this example, let us complete what will happen in the left branch also. So in the left branch, what is the overall max? That is a single node. So overall max is 9. And what is the max value you can get if you want to involve minus 10 in the path? There is just a single path which is possible, which is 9 and minus 10. So 9 and 9 would be returned. Okay. And then we can make comparisons between the overall max from left and right and all the paths possible passing through the node. So what are the paths possible passing through the node? It would be minus 10 itself, or minus 10 plus only the left hand side, like the second element from the left hand side, that is one possibility, or minus 10 plus second element from the right hand side, that is a possibility, or minus 10 plus both left and right, 9 and 30, that is also a possibility, or you take overall max from left or right, whichever is maximum. So in this case, if I involve minus 10 plus elements from both left and right, in like involving minus 10 in the path, what am I going to get? I'll get this particular path, right? But their sum would be minus 10 plus 9 plus 30, which is 39 minus 10, which is 29, which is still less than 37, and 37 would win. But 37 wouldn't win if, for example, like I had done here, I guess in the first tree, we had another additional node, which is, let's say, 11. Because if we had this 11 over here, these two values would change. I mean, here overall max would be 20, 11 plus 9, and max value possible if we include minus 10, the root node in the path, would also be 20. In that case, I would get minus 10 plus 30 plus 20, which is 50 minus 10, 40, which is more optimal. This path would win. I mean, involve 11, 9, minus 10, 10 and 20. This would be more optimal. Definitely. So that's why involving two values is important. Tracking two values is important. Just to drive home the point one more time, what I'm trying to suggest here is, if you have any node, from the left hand side you will get two values. From the right hand side, right branch, you will get two values. One is left max overall and the other is left path max. Similarly, from the right, you will get right max overall and you will get right path max. How that helps is, either your answer is the max value possible from in the left branch or the right branch. As you can notice in the given example, the right branch had the maximum path. It does not need to pass through the root. They have mentioned explicitly. In this original tree, 10 plus 20 plus 7 is the right branch and it is the answer. Okay. So either left branch or the right branch have the answer, which will be tracked by these two variables, or we want to include the root in the path. In that case, you include left path, you track the left path and right path, and then you can have multiple possibilities. So if I represent this by R, then will be four cases. Either it is only R, or it is R plus L path, or it is R plus right path, or it is both right root plus left path plus right path. That is what I am trying to say is, the possibilities would be either you involve these two, or you involve only these two, or you take this single unit, or you take this entire path. Whichever is optimal, that is, whichever is optimal from left and right branch. Okay, so for example, let's say here I had something like this, whatever. I mean, I'm just drawing out a random tree. So let's say this was the tree that I had, and right path says that this is most optimal choice, and left path says that this is the most optimal choice. So maybe our answer could be this path. You track these three, you involve the root, and you take these two. That could be a possible choice. Or maybe even more optimal than that is this particular branch right here in L max, because we are tracking everything. Max from left, max from right, overall max, and path maximums as well. It is important to note that this approach exhaustively takes care of all possible cases. I mean, think about it. When you are at a particular node, what are the possibilities? Either you include that node in the path or you don't include that node in the path. If you don't include that node in the path, either from the right branch or from the left branch, you will get the maximum possible answer, which is being tracked by these Lmax and Rmax. Or if you do include the node that we are looking at inside the path, there will be four possibilities. Either you take it alone, or you include that with some optimal path from the left branch, or you include that with some optimal path from the right branch, or you include that with both left branch and right branch, as I explained here through this example. So that is the exhaustive possibility for the problem. Include the node or don't include the node. If you are not including the node, there is no issue. You are tracking the overall max anyways from both branches. If you are including the node, you just have to take care of all possibilities, because we are also tracking path maximums as well. That is the approach. All we need to do now is implement it in code. It is tree-based code. We have a root node, so it will be recursive in nature. It should be simple to implement now that we have understood the approach. For people who are still kind of confused in the approach, I would recommend you to watch the code implementation that I do, and I'm sure that you will get complete understanding of what I was trying to explain. Let's go to the editor and try to implement the solution. So we need to return an integer, which is the max path sum, which is possible. So of course, I'll define a function which has to return a pair. Like each time we return something from a function, the helper function will define for this problem, it needs to return two values. One is overall max and one is a path max. So I can do something like return get max of root dot second. So let's say second is not second. This is first because I need to return overall max. That's what I'm interested in. Second dot second in pair represents path max, right? Please don't forget this definition. Second value that we are returning in the function is a path max involving the particular root. And the first value is the overall max, and we are interested in overall max because they have mentioned that the path does not need to pass through the root, so we need to return the overall max, hence dot first. And function would of course return a pair of integers. In it should be something like get max, and we'll just pass the tree node. So tree node pointer root. How to define this? If let's say root is null, so root is null, we don't have anything, we'll have to return there is nothing to see. So we'll have to return 0, 0. We need to be careful here. We can't return 0, 0. The second value that is being returned, which is the path minimum, that can be 0. But overall max, it cannot be 0 for the simple reason that there could be a case we have all negative nodes. So for example, let's say we had -3 or anything -3 and -2. In this case, your answer is -2. That's it, right? Because you have two nodes. They have explicitly mentioned that the path that you are returning, whatever answer you are returning, it must be non-empty. You cannot just return 0. Okay. So here answer is -2 for sure. But in my definition, in this definition, if I don't see any nodes, if I'm returning 0, 0 as the overall max is 0, that is problematic, because here for this -2, left and right pointers are null, and for both these cases, if I return 0, 0, overall max that is being sent here is 0, and I'll be returning that as the answer, which is wrong. See, this second value being 0 doesn't matter because we add it to this path value. So it will basically be -2 plus 0, which is still -2. So second value or the path value being 0 is not an issue because ultimately we are adding it to the node that we are looking at. So if the node value is negative, that will still remain negative. 0 doesn't affect that. But overall max being 0 is problem because all our nodes are negative, and if I am saying that overall max is 0, if a node is not present, that is a null case, that gives me wrong answer. So that's why instead of 0, I'll have to set them to negative infinity or int min in C++. That's it. So I'll have to set this to int min. Next, what do we have to do? We'll have some values on the left, we'll have some values from the right. So we can have a pair of integers called left vals, and left vals will be, get max from root's left side. I mean the current node, its left side. And we'll have a pair of integers called right vals as well. The right vals will be get max function operated on right side, that is the right branch. So left vals will contain L max and L path. Right vals will contain R max and R path as explained here. Then all we need to do is we can compute the path value that we can get. I mean the maximum path value that we can get. It will be maximum among either we have root value or we have root value plus left vals dot second. I mean either you take the node itself or you take the node plus the left branch path, or you take the node plus the right branch path, which is right vals dot second, or you take both, which is root val plus left vals dot second plus right vals dot second. I think that should be it. That is what we did here, right? There are these four possibilities. You take the root itself, or you take root plus left, or you take root plus right, or you take root plus left plus right, whichever is more optimal. So that's what I'm doing here in code. Either it's root value or root value plus left val, like whatever is in the left branch, it's path value, optimal path value, or just from the right, or include both left and right. Now we can compute the overall max. Overall max would be maximum of, I mean it can be path value as well. So overall max that I'm getting, it can be the path value that we have computed, or it could be left values first value, the maximum which has come from the left branch, or it could be the maximum that has come from the right branch, or it could be, I don't know, could it be something else? So overall max could be one of the path values, or it could be, okay, just a second. I don't think this we can include in path value. I mean, if I include this in path value, I cannot send it upwards. That would be an invalid path. So I need to remove this from here. And I think we should add it here, which is root val plus left vals dot second and right vals dot second. Why I did this is, if I keep root value plus the most optimal path from left and most optimal path from right, then that is not the path value, right? I cannot send it upstairs because that would be an invalid path. So there what would happen is what I was doing. So for this particular node, my path value may come out to be this, like this is the most optimal path value. But this I cannot send as a path value to this node, right? Because that would be invalid path. This is not a path. This node is repeating twice. That's the problem. So if I want to set a path value to this particular node from here, it could be either the node itself, or it could be these two, or it could be these two, because then only I can join those two nodes with this particular node for a valid path. So that's why when I'm defining the maximum, when I'm computing the maximum path value, I removed this particular path. I cannot involve the path maxes from left and right branch both, because then it would not be a valid path which I'm sending upstairs, like to the node from which the recursive call has stopped here. Right. But I can definitely involve it in overall max, because overall max is either it's one of the path values, or it's the max value coming from the left branch, or max coming from the right branch, or you involve the root and take max paths from both left and right. That could be one of the maximum value possibilities as well. And then you just return this pair. Return make pair. The first value that we're returning is overall max, right? So overall max and path value. That's it. I think this should work, because we're calling getMax from the root node itself, and we're returning the first value, which is the overall max. And when we are going inside the function, if it is a null, we return int min and 0. Int min because overall max, we cannot return 0 for a null pointer. That might affect negative values. That is a very important edge case for this problem. 0 is fine in the second value, because ultimately it will be added, because that is a path value, right? And we define two variables for left branch and right branch. And for computing the path value, we can involve only the node, or the node plus the left branch path, or the node plus right branch path. We cannot involve both left and right branch, because that would not be a valid path sum which you can send back to the recursive function. That would be an invalid path. There would be repetition of nodes, as I explained. But in overall max, we can involve either it is one of the path values, or it is max from the left branch or from the right branch, or you can involve the root node and the optimals from both left and right. Those are all the possibilities, exhaustive possibilities we have computed. This should work. Let's see. Oh, I got a wrong answer. Why? So 1, 2, 3. This is a wrong answer. Am I missing something? Okay, I think this should be sum. This is a typo. This should be fine. Yeah, let's try to solve it. Okay. So here we can do space complexity and type complexity analysis as well. So regarding space complexity analysis, whenever you do recursive calls, you are using heap memory. It's basically stack usage, recursive stack calls. So definitely you are using space which is same as the size of the tree. Explicitly, even if you try to ignore that, here we are storing left values and right values at each node. So these are some additional space that we are using. So in any case, our space complexity is big O of n. So if I just write space complexity here, it would be big O of n, and that's because of two reasons. First is we're explicitly using left values. We are storing left values and right values, that is path max and the overall max for each node. So that is additional space. It's like two storage containers for each of the n nodes. So it is big O of 2 into n, something like that. It's overall, it's big O of n only. Even if you ignore that, you are making recursive calls, which is implicitly using stack memory. So it's big O of n anyways. And the time complexity would also be big O of n, because this is a tree structure, and in the worst case, we are just going to iterate through the tree, right? So we make a call at root first, and at each place, when you are calculating the left value and right value, you are going to the left and going to the right. So it's just iterating over the tree, and you are computing and storing the values for each of the nodes that is going through each of the branches. So time complexity would also be big O of n. It's just like DFS, right? You are doing DFS on a tree. What is the time complexity? It's big O of n. You are basically recursively moving through all the nodes that are available to you. That's exactly what is happening in this problem as well. So for each node, we are making a call to the left, we are making a call to the right as we are doing here, and we are storing those values. So time complexity is big O of n, space complexity is big O of n as well. That was all for this particular problem. A very handy, a very neat problem which is asked in coding interviews. I hope you learned something. I hope you got the idea that I was trying to give in this particular video. I hope you enjoyed the video. Thanks for watching. Consider liking and subscribing to my channel for more content. See you in the next one. Bye.